applications today, and a lot of them run on Yarn, so you can run Hive on Tez and Spark both on the same sets of nodes and have Yarn manage all the containers between them. But real quick, here's what the architecture looks like. Spark runs as a Yarn app. Executors are run in Yarn containers on Yarn node managers. In EMR, we run node managers on both core and task nodes when you create a cluster. The difference is a task node doesn't have the HDFS data node. So when you scale out or scale in, you're not impacting any data in HDFS. However, most customers are storing the data in S3, so the shuffling of data in HDFS doesn't really make as much of a difference. One common question is, where is the Spark UI in Spark on Yarn? You can access it through the Resource Manager UI. If you go to the Resource Manager and find your Yarn app, there's a link for the Application Tracking UI. You can click on that. It'll proxy you through to the Spark UI, whether it's running in a driver in client mode, where it's running on the master node of your cluster, or in cluster mode, where it's running in the application master and proxying you through to that node where it is. EMR configures executors using dynamic allocation. We've been doing that for quite some time. You can still use Spark submit and specify the amount of RAM and cores for an executor. And if you had one large multi-tenant job or one large job per cluster, that would make a lot of sense. However, if you have, say, many applications running at once and you don't want to specify amount of resources for Spark to hold, dynamic allocation is very useful. So by default, we'll set the memory and the number of cores to the specifications that make most sense for the nodes in your core group. So if your core group is R3 2XL, we'll make the executor size enough where you can pack as many as possible in on those nodes. But we won't actually specify the number of them to use. Yarn will do that at runtime. So as Yarn thinks that you need more executors, it'll add more and more on. And when we talk about auto-scaling, you'll see that dynamic allocation is useful to scale out clusters and have Yarn automatically add more and more capacity as it goes through. However, if you were, say, running one large application, like, say, just a cluster that was dedicated for one Spark streaming application, you can easily create one large executor per node by using the maximize resource allocation option. That'll basically calculate what's the largest executor put on each node, and then that job will statically use it. So the number of executors will be static for the duration of that job as well. Many options to submit Spark jobs. We've got notebooks and IDEs on the cluster. We support Apache Zeppelin by default. You can, with a couple clicks, have it installed. But if you want, you can bootstrap on something like Jupyter or RStudio, depending on what your data scientists need, what your developers like. We do have the Spark Thrift server as well available. It's on the master node if you want to connect via ODBC or JDBC drivers. We don't start it by default, but you can run that command and quickly start it up and then connect to Spark SQL using those drivers. You can choose to install Oozie on the cluster. Oozie has Spark actions, so say you had a complicated processing pipeline and you wanted to create a DAG of Spark jobs and have one job wait while another part of the DAG completes and then join them later. With Oozie, you can specify these very complex processing pipelines. Also, you can use the UI and Hue on the latest EMR to actually draw out that pipeline and have a nice visual representation of what you're building for Oozie. Or you can just use the Spark Shell, Spark Submit. We also have a blog post on the AWS Big Data blog that talks about how to install a Spark job server as well. So you can provision really whatever you need using Bootstrap actions if it's not there. Actually, we could cut over real quick to my laptop to show just a couple of these UIs. As I mentioned, Zeppelin here, and the Data Zoo demo will also use Zeppelin, but you can easily create notes, you can save to Git, you can save to S3 by configuring the notebook in the Zeppelin site to save the notebook file in S3. As you can see here, lots of nice graphs and very simple visualizations. But if you want, as I mentioned before, this is running on an EMR cluster I just created. You can install RStudio and use RStudio or things like Jupyter as well. So if the tool isn't available by default, you can easily install it on as well. However, once you kind of have a production workflow, and let's say you want it to not only orchestrate running Spark jobs, but create the clusters, take the clusters down, you have coordinating, terminating and creating different resources, you probably want whatever scheduling those jobs to run outside the cluster versus, say, running Oozie on a cluster. So there's a couple options. Here's some popular ones. You can actually use the Amazon EMR step API. When you create a cluster, you can submit a step, which is a unit of work. It could be a Hive job or a Spark job, and actually have EMR tooling around it to say when this job completes, terminate the clusters. It's a very easy way to just fire off transient clusters, shut them down, or you can have a long-running cluster and submit steps to it over the lifetime of the cluster. You can also use Lambda to submit steps if you say have a job that needs to kick off certain times of day. And actually, there's an interesting blog post that Adroll post about using Lambda to fire off Spark clusters. You can use that also on like bucket preconditions, that sort of thing. Lambda is very useful and a lightweight way to kick off these jobs. Or you can use something like Data Pipeline, which is an AWS service that can orchestrate these workflows, or Airflow, Luigi, or other schedulers that you can run on EC2. One thing that we also see from just how people are leveraging Spark and AWS is really leveraging all the different storage layers where you might have certain types of customer data stored in DynamoDB with raw, maybe clickstream and S3, and being able to use Spark to join all of these disparate data sets in your analytics. EMR actually just open sourced our Hive DynamoDB connector. It's available, you can see it on AWS Labs. And it also works with Spark as well. So you can write Spark jobs against DynamoDB. You can access data in RDS or Elasticsearch using the Spark Elasticsearch connector. You can access data in Amazon Redshift using the Spark Redshift connector, Spark streaming with Apache Kafka or Amazon Kinesis, and finally accessing data in S3 using EMRFS, which is our own S3 connector that allows you to performantly access data in S3 with Spark. That's one key theme of most Spark architectures we see on AWS is decoupling your storage and your compute. S3 is designed for 11 nines of durability, extremely scalable, low cost, and is a great place to store huge data sets in a very, very durable and available way. Also, it's available across AZs. It's a regional endpoint. So if you want to, say, fire up a cluster in another AZ, you don't need to copy any data from AZ to AZ. S3 is accessible in all of them. One quick tip, though, is that for folks running something like Spark SQL, you can store your Hive tables in something like Amazon Aurora or RDS, so that if you want to shut your cluster down because your data is durable in S3, you don't need to cluster up all the time. You don't need to recreate all of your tables when you recreate your cluster. And you can configure that using values in Hive site. Just a couple tips for S3. You want to try and avoid key names in lexicographical order if you're doing very, very large scans. It'll increase your throughput and list performance. Also, utilizing compression, splittable compression, if it's appropriate depending on your file size, will really reduce the bandwidth from S3 to the cluster nodes in EC2. And using columnar formats like Parquet, and as many of you know, Spark has really great integration with Parquet to easily create data frames from Parquet files. So that's, besides just usability, performance also makes a big difference if you're just filtering down and selecting columns. Just a quick overview of Spark security, and really just focusing on encryption here. EMR, if you have, say, a HIPAA workload or requirements around encryption, it's pretty easy to encrypt all of the different data layers involved in your cluster. And that doesn't just include the disks on your cluster, it also includes S3 and internode transit. So with EMR security configurations, this is actually just a representation in the console, but it's, you can create it from the API. You can create these security configurations, specify either AWS KMS keys or encryption material providers to get keys out of, say, an HSM or some other custom key vendor that you have. You save it, you tell a cluster to use it, and EMR will encrypt all the local disks. EMRFS will use either client-side or server-side S3 encryption, depending on what you've specified, and encrypt Spark in-transit encryption as well. One feature that we recently released 2 weeks ago was auto-scaling. So when you're considering performance for your Spark jobs, and because dynamic allocation is enabled by default, you can set an auto-scaling policy with EMR where EMR provides a bunch of yarn metrics, and one useful one is, say, yarn memory percentage used. So with EMR, when you create your cluster, you can add a policy that says when yarn is using 80% of RAM, add on 2 more nodes. And in the background, EMR will configure CloudWatch alarms, use application auto-scaling, and also provide events in our console to show when your cluster is scaling up and down to scale out your cluster when it needs more nodes. When a new node manager comes up, your Spark application, if dynamic allocation is enabled, if you kept the default, will then add more executors as needed to the new capacity that's come up. One interesting thing also is that for scale down, we've implemented 2 features. One, we will scale down at the hourly boundary by default. So even if, say, your yarn memory threshold goes below with what your alarm was set for, we won't actually take any nodes away because you paid for them for an hour. What if another job comes before the hour's up? So we'll actually wait and keep track and only take nodes out and terminate them when it's nearing that hourly boundary. But another thing is you can configure it to wait for task completion. So say we won't terminate any node until all running containers on that node are finished running. And what we'll do in that case is we'll blacklist that node so no more containers can be placed on it and drain the existing work. So more of a cost saving autoscaling and then a kind of a work preserving autoscaling mode. And finally, to close, we have an upcoming feature for advanced spot provisioning. Many customers leverage Spot to save up to 80% on their compute costs. So it's a very effective way to lower your costs for your cluster. This new feature will allow you, today when you create an EMR cluster, you specify an instance group with an instance type and a bid price. With this new functionality, you'll be able to specify a list of instances with different prices and different configurations, and also different availability zones that you can launch your cluster in. And then once EMR creates the cluster, we'll look at all the different AZs, figure out what AZ is the most capacity available, and then from the instance types, what's the best value based on your inputs, and we'll create a cluster with maybe even multiple instance types within that group to use. Also to support spot block. So if you have a job that, say, will finish in a 4-hour duration and you don't want any spot interruptions, you can specify a spot block and we'll utilize spot block capacity for those instance types. Now I'll hand the mic over to Yakesa from DataZoo, and he'll run over how they use Spark for ETL and data science.
Thank you, John. Hi, guys. How are you doing? Good? Yeah, I'm having a great conference so far. Are you guys having a great conference? I can't wait for Amazon to announce their new exciting thing at the keynote. So waiting eagerly. All right, so thanks for being here. And thanks to Amazon for hosting this session. We wanted to share some of our learning experiences as we embarked on this journey to adopt Spark at DataZoo. And my name is Ekesa, and I'm joined by my colleagues, Dong and Saket. We're going to talk through our journey of Spark. A quick spiel on DataZoo, so what to expect from this session. A quick spiel, I promise to keep it short. And why Spark? What motivated us to actually use Spark? And what was it like before, right? And then the rest of the talk is split into 2 tracks. One is more engineering-oriented, data processing, kind of task-oriented workflows, and then data science workflows. So we'll look at both of them. And embedded in each section is actually a demo. And so the demo, the standard jitters might apply. So let's kudos to the engineers, and let's wish them good luck. We'll see how this works. With that said, let's get started. So who is DataZoo? Well, DataZoo is a petabyte-scale marketing platform. We were spun out of MIT labs. We operate at internet scale. The numbers speak for themselves. And in terms of what we do is we help the brands engage with the consumers along their journey. Our brands is our customers, basically the advertisers. We are in the ad tech space, as you can tell. We try to, more tactically speaking, we try to maximize the return on investment for our advertisers. So how we might do that, I'm going to cover that in the next couple of slides. Quick run through the numbers. We have a real-time engine capability, which processes about 2 million transactions a second. So this talk is about an hour-long talk. So during this talk, our system would process about 7.2 billion transactions as I'm standing here. Our systems collect about 180 terabytes of logs every day. And we analyze about 2 petabytes of data on a daily basis. And we operate out of 13 different regions and data centers. It's a 24/7 operations. The big meta point from this slide, really, is we collect and store and analyze large volumes of data, like most of you. And what we need to do our job well is a reliable, secure, and elastic platform that can handle iterative and interactive workloads, right? And of course, we need a heavy dose of automation. Without automation, you can't run this scale of jobs, right? So real-time bidding. So I said we help our brands engage with their customers. So how do we do that? Well, we do that with our real-time capabilities. So I'm not going to talk through each block in this picture, but here is I'm going to give you more concrete examples so it's more tangible. Let's say you are looking for a car. You might go on some websites. You might put in some parameters. You put in the car manufacturer, style, price. You might do some side-by-side comparisons. You might look for deals in the internet in your neighborhood. As you're doing that, you're dropping hints to the medium and the websites that you are perhaps searching on, might have some ad slots on the side that get auctioned off in real time. And real-time engines like ours, we bid for those opportunities. We are not the only one. We have competition. And the real-time auctioning of ad slots at an impression level is called real-time bidding. It's basically that's it in a nutshell. The one thing that I want you to note from this picture is that as we are bidding out there in the internet, we are generating lots of events. And these events are, hey, I bid for this user at this price, and I won the auction. Or I bid for this user at this price, I didn't win the auction. We need to collect this data so we know to adjust these bidding strategies in real time, right? That's where data science comes in. So there is a lot of logging going on, and the real-time system spews out lots of data. That's where the 180 terabytes come from. And we have our data pipeline runs through these logs on a daily basis and looking for the tidbits of information and extracting nuggets of wisdom so we can feed it back into real-time engine so it can change its bidding strategies on the fly. All right, so why Spark? Spark was, before Spark, I'm going to show you a slide how it looked like. We were a heavy MapReduce job, heavy MapReduce platform, as well as we had, we still have massively parallel databases, MPP databases, right, to do our ETL. So we have ETLs that are going on in MapReduce, and we have ETLs going on in our MPP databases. But at the scale of our data, it wasn't, number one, cost effective, and number two, wasn't meeting the SLAs. So we were under a time crunch to process this volume of data. So, and most of you are familiar with the big data space. You know all the technology offerings, so MapReduce, Hive, and all the other things. The big appeal of Spark is really its performance, its speed, right? It gets its performance from a couple of ways, right? One is in-memory data structures and computations. And number two, like John mentioned, the DAG, the directed acyclical graph. If you look at a traditional database execution plan, it looks like a tree execution plan. It's a set of instructions formed as a tree. That's a directed acyclical graph, right? And then it knows to avoid a shuffle when the data has already been partitioned the way it's needed. So overall, Spark is very fast. I'm not going to give you a lot of this topic has been talked about several times. Contrast that with the MapReduce, where there's a lot of disk I/O going on within the mapper, between the mapper and the reducer. And when it kicks off a shuffle phase, there's a lot of data transfer over the internet or over the network. So a lot of disk I/O going on, a lot of bytes moving around, not participating in the compute function. So that's where we started to scratch our head and figure out, how do we do this? And then the other thing is, it speaks your language. You have Java, Scala, perhaps for your data engineering tasks, Python and R, more for the analysis, if that's what you choose. But the best part is the following. They all interoperate well together, unlike its predecessors, right? So you can construct your data sets or data frames in one language, leave it in memory, let the other one pick up from there. It's very well integrated. Streaming use cases, of course, it comes built in with the streaming support, which is great. Spark is certainly appealing, no questions, right? But Spark on EMR makes it compelling. Here is why. Amazon EMR is a very mature, elastic, and secure platform. You can spin it up and down as much as you need. And John talked about Spark instances and auto-scaling features. And then it's a decoupled storage and compute. You only pull in the data that you need for your job, right? Unlike traditional databases where you have to load the whole thing into its database structures. In EMR, you just bring in the data you need for your analysis. So for these reasons, and then now throw in the Spark instances, it makes it much more appealing in terms of the TCO, the total cost of ownership, right? So for these reasons, Spark on EMR, you can't ignore anymore. So this is how our architecture looked like before we embarked on Spark. So I talked about real-time bidding, generating lots of events. And we bring all those events through Kinesis endpoint. That hasn't changed. That still is the same. And we store all the data in S3. That's our archive. And then we have these 3 big MapReduce jobs. Each one runs sequentially, one after the other, reading and writing out of S3, right? Now you can tell there's a lot of disk I/O going on, right? So this is where it wasn't as efficient as we wanted it to be. And then, of course, we have the data analytics. See that little Giphy that's bouncing up and down? That's our analytics engine. That's data science producing signals back into the real-time engine. And Saket is going to cover a little bit of that coming up. One thing I want to mention before I leave this slide is the ecosystem of Amazon services. S3, EMR, they're all great. But the other things that actually glue everything together, like the IAMs, the VPCs, the Direct Connect, the DynamoDB, they are vital to run any production workloads as well. I just want to call that out. All right, so that's the picture we had before, right? That's transitioning out. So we thought long and hard, how do we do this? So our data science team actually started exploring new ways to write their algorithms. And then they ran into Spark. And then they followed by engineering team. I have the pleasure of working with both teams, so we bounce ideas off of each other. When the data science team started working with Spark, we said, hey, maybe we should give it a try. Traditional ETL, you think of a database, right? Informatica and whatever tools work for you, classic database workloads. But then we said, why don't we try Spark? So we embarked on this journey. Nothing changed on the left-hand side. It's still Kinesis. Nothing changed on the right-hand side. It is still S3. But how we process the data changed. We restructured our workflows into Spark jobs. One iterates on the other, right? It's an iterative workflow. All the data is stored in memory. We iterate over and over again until we get the final result, dump it in S3, and it starts all over again, right? But then, at the time that we were building this Spark pipeline, we also thought about, hey, we have multiple teams here, right? We have engineering teams, multiple of them. We have data science team. How do we make this code more reusable across the board? So what we did was we created we refactored the code base such that the foundation or the common backend is factored out of that application logic. So we have one system that it handles all the infrastructure level things like logging, monitoring, alerting, auto-scaling, and things like that. Integration with Lambda, John mentioned this one, so we use that as well. You can fire up a cluster automatically using Lambda. So we kind of refactored all of those things and pushed it one layer down for maximum code reuse. So that's another team doing it. And then we support all those libraries on top of that engine. So the foundation doesn't care which library you use. You can use Spark SQL. You can use Spark MLlib. You can use anything you want. And by the way, that's where we expect the innovation to continue. That's why I have ... right? While the EMR and the common backend stays the same, we expect a lot of innovation to come in that tier. So that's basically the picture. Now let's look at how that simplified our lives, right? Now you can compare and contrast. What happened to that picture with big 3 MapReduce jobs, processing a lot of disk, right? Got simplified. Very efficient in terms of compute, in terms of processing times, a much simplified architecture, and we have even refactored the code so there's just one code base running all different applications. With that said, now let me invite up Dong, and he's going to walk us through the ETL part of the workload.
All right. Thank you, Kesa. So I'm going to talk to you about the ETL pipeline at Data Zoo. We are looking at a typical pipeline. This is also one of our most critical pipeline. On the top left side, you are looking at event data. That is billions of records per day. There are our impressions, attributions, events. On the bottom left, you are looking at the reference data. Those are campaign configurations, audience retargeting. Such data can be also large. Some of those configurations can easily be 500 million records, so that's not trivial either. On the right side, that's the product of the ETL process. So you're looking at application logs, exception data sets, but most importantly, our reporting data sets. In the middle is our ETL engine, and I'm going to describe to you our ever journey in finding a better ETL engine. About 4 or 5 years ago, we adopted MPP database. We run MPP database in our colo. It served us well. However, we quickly ran into some issues. We have hardware stability issues. At any point of time, we cannot be sure a single cluster can support all of our production load. We ended up provisioning multiple clusters that compounded our production problems. We have 2 DBAs constantly watching all the 2 clusters, a lot of heavy maintenance. We have unpredictable work time. We don't know how long each pipeline is going to finish. And it's not elastic. It takes us months to plan and execute a cluster expansion. So that is not working well. The next step, we looked at running the MPP at the cloud environment. We couldn't get the multi-node working at the time in cloud, in AWS, some networking issues. So we ended up with a single node MPP running in AWS and with the largest I2 instance we can get at a time. It solved a lot of problems. It's stable. We have predictable execution time. But we still have 2 problems. We found out that it's still a fixed capacity. So if we project business is going to grow 3 times, it's going to exhaust all the capacities that the I2 instance node can support. And we also found our application stack is written for the hosted solution and does not take advantage of all the cloud can offer. As Akasa mentioned, that our data science team started to look into Spark, and we have also a lot of in-house expertise in EMR. So we decided to look at Spark running on EMR. We changed our pattern when we adopted Spark on EMR. Previously, we always have a persistent cluster, MPP database cluster running either in hosted solution or running in cloud. On the Spark for EMR, we're actually launching transient clusters. We only start clusters when we accumulate sufficient batch data, and then we run through the cluster, and when it's finished, we terminate the cluster. That is significant for 2 reasons. We no longer have stability maintenance issues. Any problems coming up, we just dispose the cluster and launch a new one. And then it has significant cost savings for us because we're not running a permanent cluster all the time. So in this slide, I'm going to show you some of the cost performance benchmarks. You're looking at the 3 scenarios. The MPP running in colo. You can see it's a large installation, 48 nodes, and we have multiple of them. Then we have the single node MPP running in AWS, and then we have Spark running on EMR, running on different cluster size and instance types. I'll let you chew on these numbers, but I'll just quickly point out some key findings here. If you look at the execution time, the execution time on an MTP database is hugely variable. We just cannot know exactly when it will finish. But if you look at the Spark, it is very, very consistent. It's almost on the dot. It's always within a minute. It's a very, very stable environment. And then if you look at the monthly cost, on top of the 75% drop we can get from moving MPP from hosted solution to AWS, when we moved to Spark, we're actually getting another 80 to 90% savings. Such significant savings is coming from the fact that I mentioned previously that we are using the transient cluster, but also we are using a much smaller cluster compared to MPP. And all these numbers calculated for Spark are actually on-demand instances. So when we switch to Spot instances, we can get additional savings. In this slide, I'm showing some scalability tests. On the left side, we are looking at execution time and the cost for a different sized cluster. This is for the same data set, but we are creating different sizes of cluster from 2 core nodes up to 6 core nodes. We are looking at a range of possibilities. We get a larger drop in the execution time on the lower end and a diminishing returns on the higher end. So this gives us the possibility that you look at different types of the pipeline and pick your sweet spot. If you have a very tight SOA requirement, you actually want to run a larger cluster to ensure you meet that SOA. While if you have the pipeline that doesn't have such a tight SOA requirement, you may want to use a more cost-effective cluster. On the right side, what we are looking at is a study of what if our data volume becomes 10 times. So we stage a data set in increments from 1 times, 2 times, all the way to 10 times. And with each increment of the data set, we added 6 core nodes to the cluster. So an ideal case showed on the blue line is that you would see a flat line of the execution time. We actually found out somewhat nonlinear scalability. The key point here is actually it is relatively very, very easy to set this up on EMR. We can run these experiments in a couple of hours, and we can say confidently to our business that what if our business grows 10 times, what are the possible problems we will face, and what kind of engineering efforts we need to put in there to reach that scalability. So I'm going to share some tips. So Spark SQL, you want to use the broadcast hash join. If you're not familiar with it, it is basically you have these very small dimension tables. You want to replicate them across the executors. And for the large fact tables, you would partition them and spread evenly across the executors. This was not available on our MPP database. It is somewhat hard to enable it on Spark 1.6, and it's very easy in 2.0. So if you are still running 1.6, it may be time to consider upgrading. We look at a UDF. As compared to some of the traditional databases where when you switch from SQL engine to a procedural execution language engine, you get some performance penalties. We find that Spark does not incur that penalty. In fact, in some cases, you get a better performance. But we primarily use UDF for readability, better modularity, and testability, which I will show in the demo. We are able to execute very complex SQLs on Spark. We're actually taking 250 lines of SQL directly from our MPP code database and just dropped it into Spark. With the minor changes to the function names, it just runs. So this is great. While we also find out that Spark has a limit of the most optimized code. With Spark 2.0, the whole stage code chain, we actually found there's a 64K maximum limit. When you exceed that limit, you don't get optimized code. What we do is use some tried hard database techniques, just materialize some section of the code into files. We write out as Parquet and read back in. In that way, you would collapse the DAG, and it might become a much simpler query so that you get all the optimized code. Always watch out for your bottlenecks. We found that you want to really scrutinize your actions on the Spark driver that is not parallelized. So any actions you do there could be a bottleneck. Sometimes the bottleneck is outside Spark. We have seen JDBC connections, sometimes even EMR FS having not sufficient capacity provisioned for the DynamoDB. So big lessons learned. Forklifting from hosted solution to cloud sometimes works. We have mixed results. In our case, we actually have to rewrite our entire application stack. The rewrite gives us about 80% code reductions with the Scala. And we also increased the testing coverage. So in our case, we actually have to rewrite the stat. You want to rethink about the ETL processing. As I mentioned, the Spark SQL is rock solid, and the 2.0 supports most of the 2003 SQL standard with some of the advanced features. We found out that most of our ETL pipeline, we don't need MapReduce anymore. MapReduce becomes mostly a niche case. You want to do the streamline your processing. In our MPP database, what we did is we would mark the staging tables with all the exceptions and copy those exceptions into exception table and delete them from staging table. That is, again, a lot of I/O back and forth. So in the Spark, what we did is as you read data into the memory, we would mark those records with select statement so that we'll all collect all the exceptions into a single column. And when you write out data, when that column is null, then you would write out to the reporting data set. And that column is not null, you would write to the exception data set. You want to rethink about your in-memory processing. Spark is a great in-memory engine, but you want to look after all the incoming data footprints, particularly the dimension table. I mentioned that some of our dimension tables are non-trivial. And we actually, instead of what MPP database did, where we have the table staged for all pipelines, in the Spark ETL pipeline, we actually filtered the dimension both horizontally and vertically so that we are only getting the data we need. Control your unnecessary joins. Use your joins effectively. Use it to validate foreign keys as well as project columns for downstream processing. And last but not least, EMR is our excellent common backend. We took EMR and just plug in the default configurations with the maximized resource allocation. And we just produced sufficient performance for us. We didn't do any performance tuning required. The only thing we looked at is making sure broadcast hash join is working for us. As we also mentioned previously, EMR gave us very consistent performance. So with that, please wish me luck. I'm going to start to do a demo. All right, I think we are. Oh, sorry. As a first hiccup, I lost the VPN connection. So what you're looking at is a Zeppelin notebook. For those of you who are not familiar with Zeppelin, it is a web-based interface where you can connect directly to Spark and then run your interactive data analysis. We started a EMR cluster with Spark and the Zeppelin all installed. So I'm going to kick this off as I talk. So in this demo, you're looking at, we're going to load up the schema. We're going to load up some of the fact tables and the dimensions. We have a big impression table that is about 12 million records. And then you could get 17 different dimension tables. In the next section, we are showcasing the Spark join. You have an impression table that is joined to all the 17 different dimensions. Meanwhile, during these dimensions, we also want to make sure you're doing these exception checkings along the way so that for all the foreign keys validations you are looking at, you would join to the dimensions, and if you don't find your corresponding records in the dimension table, you'll just mark them as foreign key violations, and then you just collect them, collapse them into a single column. What we are seeing here is a physical plan. It's an execution plan for the 17-way joins. You can see all the broadcast hash joins just happens 17 times. And then we found 3 exceptions out of the 12 million records. The next section I'm going to show is the UDF. Before jumping into that, I'm going to show you what we had before. What we had before is a very complex SQL execution. we are doing some very complex spend calculations. What you see here is a iterative query blocks. Each query blocks calculates certain columns that then feed into the next query blocks. As you can see here, this second query blocks, it takes in some of the columns that's calculated in the first query blocks, calculating some additional columns, and then those columns then fed into the next query block. This big giant section repeats several times. This is not we cannot unit test this section, and we end up building a very complex integration test for it. With Spark, we are able to rewrite it as a Scala UDF. First of all, we take advantage of the versatile map data type. We can use the key value data store so that you have the spend component name as the key and the spend number as the value. In addition, we can rewrite all these SQL sections as Scala, and you can see that it's actually a direct translation of the SQL into Scala code. With this, we can run, we would register the UDF, and we would run the query by invoking the UDF section. I'm not going to show you all the 12 million records, but the top 20 records here, you can see the map of a key and the value data set all generated from this UDF. So with that, I'm going to hand off to my colleague Saket to talk about data science at the DataZoo.
All right. OK, so I'm Saket, and I am the senior principal data scientist at DataZoo. And what my team works on is basically training machine learning algorithms that goes and buys online ads on the internet. So basically, when we basically serve ads for almost like thousands of advertisers, and what our algorithms are doing is trying to find, when a user comes in, tries to find which advertiser's ads fits this user the most, and what's the probability that this user is going to click on the ad or show a positive intent for the ad. And to do this, we use a lot of data, as we have been seeing. So let me just explain how the process works. Whenever we serve an ad on the internet, like whenever you see a banner ad or a video or ad on YouTube and so on, we create a log line in our database. And those log lines are called as impressions. Now, whenever a user reacts positively to any of our impressions, like maybe click on the ad or maybe go to the advertiser's web page and buy something or check something out, we call that as a positive signal on the internet, and we call it as attributions. So using Spark, what we do is we are running a huge join between all the impressions that we are serving and all the positive signals we are getting on the internet. And this generates a data set where each impression either is a positive or a negative that can be used in a machine learning classifier. Now we give this data to our training models. We create classifiers out of them. The classifiers, what they do is whenever a user comes online and goes to a web page, it tries to predict what's the probability that this user will have a positive signal when I show an ad to him or her. Once we create the models, we evaluate the models before pushing it in production. So we try to see if the models actually are able to predict conversions or not. And if the models are good, we will push it to S3, at which time the real-time bidding system will pick up the models and use them for buying more ads. That generates more data, and again, we'll train our classifiers using the data. So I just wanted to appreciate why this problem is difficult. And I'm pretty sure all of you work with a lot of data. So what we have here is every day, we have to use 2 petabytes of data and train machine learning algorithms from it. Because all the ads that we are serving on the internet, we are collecting all this data and we are training classifiers from it, right? So it's a lot of data. And we are training thousands of classifiers every day for all the different advertisers that we are serving ads to. Moreover, the real-time bidding system is making almost 2 million decisions every second. Every time a person goes on the web page, we are making a decision to show which ad to show to that person and how much do we want to pay for that ad. So we are making 2 million decisions every second on that person. So the system has to be really fast in training as well as during the evaluation time. Secondly, we wanted to create an unattended system. So we are not running these jobs every day. What we wanted to do was the system automatically just collects the data from the internet, from the ads that were served yesterday, creates the new models, again goes out, buys new ads using those models, again creates these, again gets the data, creates models, and keeps on going. So we wanted to create an unattended system, so we don't have to maintain it. We just have to keep on pushing new code, and it just works. And thirdly, we are in the industry of online ad market. So there are a lot of competitors who are trying to bid on these ads. It's like an auction where everyone is trying to bid on the ad. The person who bids the highest gets to win the ad, right? So we want to have state-of-the-art algorithms, because if our competitor has a better algorithm than us, they will be able to buy more efficient ads than us. So we have to keep on adapting to the customer's requirements really quickly. So what I'm going to show in the next few slides is why we are so excited about Spark at DataZoo for the data science tasks. So we ran some benchmarks using Spark. We used 3 algorithms from the MLlib library. And the first thing we saw was Spark trains in linear time. There's not a lot of overhead when we are training models on Spark. They are really well tuned. And this is very important for us because we have thousands of advertisers we serve to, right? There are some advertisers that are spending hundreds of dollars per day. There are some that are spending thousands, some that are spending tens of thousands of dollars per day. So the largest advertiser generates the most data to train the classifier, and that's the bottleneck in our system. And we have to train our classifiers in linear fashion because as we get more data and as the business scales, we just want our algorithms to scale with that. Secondly, as I said, that we are making almost 2 million decisions every second. So we want 2 things in our models. Firstly, we want our models to have a very small memory footprint so that they can stay in a very fast memory. And secondly, the evaluation time or the bidding time has to be really small. So what we found was Spark's performance was really good out of the box. Now you can see that the DataZoo models did perform well in these tests, but we have spent like 7 years on optimizing these algorithms over and over again to make them as efficient as possible. And Spark's performance out here is out of the box. And we found that it was feasible for us to use the Spark models directly out of the box, which is pretty cool. So just wanted to go over the big picture of what we found when we were using Spark. Now, first of all, now we have a homogeneous platform where our ETL processes are using Spark, and our machine learning processes are also using Spark. So all the data flows in memory, and we are training models out of it. Secondly, Spark works really well on EMR out of the box, which is really important for us because most of our platform is using EMR, and Spark really works well on that. We needed very little code to create these classifiers. Like we needed, and I'll show a demo for that. But it was really easy to implement the Spark architecture on the existing platform. And lastly, Spark did provide us stability to actually create an unattended system that just works well. Having said that, I'm going to go to the demo. All right. Just going to run this because it takes a while to. Now remember I said that we have all the impressions that we serve, and then we also get positive signals on the internet. Now to combine all the data together, which is called the attribution job, you can see that we can do the entire thing in one SQL statement out here on Spark, which is very cool. Once we create the data set, now we have a data set that we can use in machine learning. What we are going to do is we are going to divide the data into 2 parts, the training data, which is 70% of the data, and the testing data, which is 30% of the data. Now, this is really interesting. So what happens is once we have the test set, we are going to create a Spark pipeline to train our models. What I mean here is I'm going to define different stages. Like the first stage is to get the data. The second stage is to pre-process the features. So you can use like feature selection algorithms on it. You can use top K transforms and stuff like that in this phase. And you pre-process all your features that you're going to use. In the third stage, you are going to assemble all the features back together to create a data set. And in the fourth stage, you are going to select a classifier. Now, as a data scientist, I want to test using many different classifiers. And using this pipeline architecture, I can just replace any classifier here and create different pipelines for different campaigns that we are working with. And finally, I put these stages into a pipeline. Now, here, the trainings for the models are going on. This is live. So we created a train data set before, right? So what I'm going to do is I'm going to convert the train data set into Spark readable format, which is called as train ML dataset. And all I'm going to say is I'm going to fit this data into the pipeline. So now the train data set actually gets all the data together, goes through the pre-processing phase where I'm going to run feature selection algorithms and key transforms and stuff like that on it. Then I'm going to reassemble all the features together and run classifiers on it. And all that can be done in this one step. Now, the training is going on. So once the model is trained, we also want to evaluate if the model is good or not. Because if the model is not able to predict if a person is going to have positive signal or not, it's useless to me, right? So we are going to run an evaluation phase where I'm going to take the 30% of the data, create it into a Spark readable format, and then pass it through the trained model. So for the 30% of the data, it's going to go and try to predict probability of conversion for each of the rows. And I also know the ground truth for them. So I know if my predictions are correct or not. So once the predictions are done, okay, so our training job is finished, and now the prediction job is running. Once the predictions are done, I'm going to find the AUC, which is a measure of accuracy for the classifiers. So if it tends close to 100%, that means that my classifier is good at predicting a conversion. If it tends close to 50%, it means that it's a random classifier. So the training is going on right now. The testing is going on right now. And once this job is done, I expect to see what the accuracy of my classifier is. It should be done in a few seconds. So the big picture for this demo is you can see that just using this small amount of code, what I was running here was the data that was passed through Dong's ETL. So it was 12 million records that passed through an ETL process during the demo that went through the attribution phase. I created a pipeline for training the data set. The whole training, 12 million rows actually went through a training model, created a model, and now you can see that it's going through the classification phase, and any minute now it should be done and give me a ROC area, which is right here. And not bad, I guess. So that concludes our talk. Do we have time for Q&A?